Who am I? I'm Bradford Cross. History is I've been doing functional programming for about like 15 years, starting in around 2005 to 2009 timeframe. I was originally investigating it myself with some stuff that I was working on, and then when I went to Google for a couple of years, I saw these really huge legacy systems written in C++ and Java and JavaScript. I was on a special team called the Test Mercenaries. We would go around and try to refactor and bring under test some of the most unwieldy giant legacy code bases that were lurking around. This was maps, the Borg code base, which was the predecessor to Kubernetes, um, all the way to search and so on, right? And like we really helped to influence things a lot, to turning teams that would ship maybe once every 6 months into teams that would ship weekly, had really great test coverage, fine-grained decomposition of the code base instead of like large monolithic functions and whatnot. We really helped to get things going faster. And through that experience, combined with my own investigations that I'd been doing on the side, I became like super sold that a functional approach is really the way to go. Like that's clearly the way to build software with smaller teams, go faster, smaller code bases, like way easier to maintain, way nicer for production. Tons of stuff I'm going to go into as far as the reasons why. But really, it was my own work on the side combined with what I was seeing live at Google, especially with these really huge, like giant production systems, that inspired me to start thinking this way. I left in '09. I started doing startups, and I did my first company that was the first AI startup ever in Y Combinator back then. That's called Prismatic. Um, we were basically like Clojure, Hadoop, and Rails, kind of, I would say, right? Built on early AWS. And it was, at the time, like a pretty like state of the art stack, I would say. Like Rails was probably a solid thing to be using for building a web app. Um, Hadoop is what a lot of people were using to do big batch processing jobs. Everybody was starting to build on AWS, so we were kind of this like state of the art stack. And Clojure was what I used to write everything for all the core modeling and whatnot that ran on top of Hadoop on all the JVM stuff. What I found though was it kind of sucked being bound to these big monolithic frameworky things. So I didn't like how I would do stuff and throw it over the wall to the Rails side. And I also didn't like being bound to Hadoop, which is like this big, unwieldy, like crappy thing. And the MapReduce paradigm is obviously very constraining. And I felt like, man, like it kind of sucks being bound to these giant pieces of like batch processing and like app infrastructure. So then when we built Prismatic, which was my second startup, we built the thing entirely in Clojure, like really, really nice, like bottom up design. Like the whole team was on board, like from the ground up, like everything was all Clojure. It was really sort of like, I think, a canonical example of how you should be doing this. It's kind of like a baby WhatsApp, like pretty small team, pretty tight code base. Like that's how it should really be. You should be able to build big, big stuff with pretty small teams. There's some key abstractions that we did that allowed us, to really build a massive amount of functionality with a pretty small engineering team. Then after Prismatic, right? So we sold Prismatic to LinkedIn in 2015. Then I started doing startup studios, and I did 4 startups there at this entity that I called CEAI, Central European Artificial Intelligence, in a network of 4 cities in Central Europe, Czech Republic, and Slovakia. So we grew to basically 150 people in about 2-3 years. We built 4 startups, had a solid exit. Could have done better, but that's a long story. Ultimately, though, technically what happened is that we used Scala, we used JavaScript, we used Python, we used like all the normal stuff that people would use. Like I allowed the team to just do whatever they wanted to do. I didn't try to like really impose my technical vision on how we did things. And frankly, I think it sucked. I think it was, the velocity was mostly really slow. There was one project in particular, one company that like just had constant technical issues, way too little done for the size of the team, legacy kind of systems from day one. Like what you wrote yesterday is today's legacy, basically. Really needing to rewrite, refactor, like exchanging frameworks around, everything else. It was awful. Production issues, performance issues. It really was unpleasant. And a lot of it was really on that Scala side, right? And I saw a lot of really bad kind of Scala patterns from that. And then on my new studio, Two Lions, we had a false start with our first company that we're working on, Warmer, which is still in stealth, where we had a team that we allowed to build everything in Node and JS. And what we found there was, again, like this framework happy culture, like adding frameworks even for workers and stuff like that, where it should really just be like, you're running a function in a thread. Like you don't need to have some special framework for workers for that. Like you should be able to distribute that over on top of the cloud primitives like real easily. And we were seeing too much code, too little getting done, too slowly. And frankly, I just got really pissed off, and I was like, we're not going to win like this. Because as a startup, you need to be able to punch above your weight class. You need to be able to get 10 times, 100 times, 1,000 times done what a normal team that size should get done. The way you do it is like, A, you have to work your ass off, work all the time, and always be producing output, obviously. Like you can't just work a normal 9 to 5 and expect that you're going to have this huge outcome. But also, like, you've got to be working smarter. And so the smarter part from an engineering perspective means that you can't have like massive amounts of stuff that you're dragging in with all these frameworks and everything in order to just get basic shit done. You can't have 3, 4, 5 people in a very small startup, and already you're going really slow, and you're taking a long time to take decisions about which framework to use, and you're deciding, oh no, this there's a problem with this, let me switch it out with this other framework and all this stuff. You can't do that. That's this sort of legacy, like big organization way of behaving. And unfortunately, that's like what a lot of people are doing right now. They jump to that first, right? They don't start building what they need bottom up, right? With the primitives that are available in a modern functional language and the primitives that are available in the cloud. And that's really the way to do this shit, is like you have cloud primitives and you have FP primitives, and that's what we're going to build everything on top of. We're not going to think about all the different ecosystem of all these crazy frameworks and everything. We're going to build what we need, and when we really need to, we'll reach for a library. Very rarely do we want like frameworks. So what are the problems? The productivity sucks with this other paradigm, right? Like the size of the team, the size of the code base, the pace of what you develop, they all suck. It's just disappointment all around. And then the manageability sucks. That's the other big problem. So, I believe in a model where like the engineers are the SREs, like the config is expressed in the code. You don't have other weird YAML files and shit. It's easier to instrument and debug. You don't have these extreme brittleness issues where, you change something, shit's broken, you don't know why, you don't know what's happening in this other weird framework. Like it's all instrumentable in much easier ways. You're not like coupling everything to Datadog or some other weird service just to like instrument and observe your code. Like it's really about going faster and making stuff that's like manageable in production and maintainable and extendable, and doesn't like get you into this horrible gridlock once you have something like materially large that you've built. All of a sudden you can't go fast anymore and build new stuff, which really, is kind of the lifeblood of a startup. Startups are about innovation, and big companies kind of should be building new stuff too, but especially for startups, like if you're stuck and you can't keep innovating and rolling out new stuff and you're like really stuck where you are, you're kind of hosed. Like the whole thing's just gonna fail. Like you're very unlikely to have success. I think that for a lot of companies, depending on the scale of the company and where it's off by like a factor of 10, 100, or 1,000. So for some of the really big tech companies, like the big fangs, like Facebook, Google, etc., I think there's actually a case to be made where they might be like a full-blown 1,000x off from like how many engineers they have, how many lines of code they have, etc. Like really, like it's really bad. This is extreme. The problem is very extreme. I don't want to downplay it. It's really extreme. And for a small startups, like it's probably still off by a factor of 10 for a lot of places, right? So it's a big, big problem that I'm talking about. It's not a small problem. I think everybody, every startup especially, should be looking to pull a WhatsApp, right? You should be looking to scale like crazy without scaling your headcount like crazy. And the way to do it is this, what I'm talking about today, right? This is the way you should be thinking about it. Bottom up programming, fine grained abstractions, and composability, not anything else. This is like the only way to do it. I think you go faster, you ship more things incrementally by making use of things you already have. So you add a new piece of functionality by just adding this one function and composing together all these other functions that you already have. You're not doing a big refactoring and pulling these things out and then, oh, now let me do this and this. Oh, now I have this whole other object. It's like, no, like I already have all this stuff and I can quickly see how I can compose all the abstractions I already have, add this one new thing, boom. Now, all of a sudden, I do this radically new thing that seemed like it was a huge amount of work, but I was able to do it in only a couple of hours because I just only had to write this one new function and then something else that composed that with a bunch of other stuff, and then boom, now off I go. That's really the power of it, is like you get this, instead of a legacy system effect where the more you write, the more inertia there is and the more expensive change is, the more you write, you're compounding this super valuable library of abstractions that you have that you can wield, and you actually get faster instead of slower, which is really interesting. So totally different approach. I think another point is like avoiding the frameworkification and vendorification, I would say. So I talk about this a lot. So frameworkification is this whole like, I like to talk about don't call us, we'll call you, right? Like do libraries, don't do frameworks. Like don't buy into this model where tons of magic happens and then you just write something that gets called by the magic and you don't know what's happening and then shit's broken and you're like, I don't know what's happening. Like I just wrote this thing and something's wrong in the machinery back here. Like it's really not the best, I don't think. And then what's happened in recent times is even worse because now you have this sort of vendorification of this stuff. So you have these gnarly frameworks, but now they've been turned into SaaS tools. And so people are hard coding in these SaaS tools that you have to pay for and that don't scale like economically with what you're doing. So now you're building your startup, you have some success, boom, you're scaling up, and then you're looking at your bill to like all these different vendors and you're like, holy crap, this is really expensive. And that's also problematic. And that's also even more difficult to debug sometimes if you have problems in production. I mean, the nice side of it on the flip is that these guys are doing all the like production stuff for you, right? Like, so they're maintaining it. They're making sure that the things are up and that you're not having all these issues. So you're punting some of the production stuff to them. But if you do have issues, the problem is that now you have like tremendous opacity, like so it's very opaque what's going on. So it's mostly good from a production perspective, but there's bad to that too. The other piece that I wanted to mention is basically this micro productivity that you can sometimes experience. What's really nice about Clojure is that the data structure library design was very good. And the way that the data structure literals work with destructuring is very good and unique. And so it makes you very, very productive in these small micro ways that add up a lot that you might not necessarily think of. Just when you're doing list processing or writing functions or whatever, the way that you use destructuring and work with the data structures makes you really really productive. It basically cuts out tons of code. Now, the alternative in like the, standard programming language land is that people are basically using increasingly sophisticated IDEs that like just generate a ton of this shit. That kind of sucks in my opinion, because it's like, okay, the language is inferior, so let's like build these gnarlier and gnarlier tools around the language to like auto generate all this boilerplate stuff. It's like, let's just not have the boilerplate stuff in the language instead of doing that. That's my approach. Okay, now let's talk about why is Clojure awesome, and then I'll end with some examples from Prismatic in the past. Clojure is awesome because it's a practical Lisp. It has awesome data structures, like I just mentioned, that goes together with data structure literals and destructuring that functions well with those literals. And like that whole suite of the data structures, the literals and the destructuring is just awesome. Like I think it's probably the best of any programming language in human history as far as I'm concerned. So that piece of it really shines. It has a very practical approach to mutability by dropping down to Java or JavaScript. I think in FP, a lot of people became for a while like overly obsessed with immutability. My view on this is, if I'm not going to edit this thing from multiple threads concurrently, why do I care? So maybe sometimes there is a time when I should be using a mutable data structure or something within a function. And it's very easy to do so if I want to, by dipping down and using the data structures that underlie Java and JavaScript instead of working with the functional and immutable data structures in Clojure. So that's also very practical, I think. And then it's a focus on simplicity and bottom up in the spirit of old school Lisp, like old school Scheme, Smalltalk, etc. Really like keep it simple. Don't bloat everything like crazy. I mean, that's what happened with Lisp, with Common Lisp, is it got gnarly. It just kept on expanding, and then people didn't really want to use it. It's so complicated. I think that's very important. Clojure has kept it really simple in a way that almost nothing else has. There's been a couple of other recent programming languages that are non-functional, like Go, that have tried to take this like extreme simplicity ethos, which I'm a huge fan of. But I obviously want to see it done with FP. And then last piece that I think is awesome is the REPL culture. Being able to quickly prototype things at the REPL and play around, and also the way you work with production with the REPL, man, it is special. Like having the REPL for both going fast, prototyping, like developing shit, and then also having the REPL for like war mode, like production debugging and whatnot, like equally super powerful, equally amazing. Like it's really special to be working at the Clojure REPL, like for real. Like it's not well understood by people who haven't enjoyed that. When I talk to old friends, like I talked to one of my best people in Prismatic, sort of overall tech lead recently, who hasn't been working in Clojure for a while. And he was like, yeah, man, I really miss the REPL. He's doing stuff in Scala, and they've made great strides in Scala 3 to try to simplify stuff a lot. And you can choose to not use a lot of the stuff in Scala that makes it more complicated, let's say. So you do more of a simple, like old school ML, not machine learning, but ML, like programming language type approach. And that's cool, but you still don't have the REPL. So there's things that you miss. But the REPL is like, everybody will tell you, like, man, I miss it. If they worked in it and they're not working it anymore. So that's special. Okay, I want to talk about two examples of bottom-up abstraction, both of which will have saved a tremendous amount of code and heartache in real practical terms when it comes to developing production systems. Both of these are from Prismatic back in the day. One's called Schema, the other one's called Graph. So first, Schema, a lot of people talk about when you have a dynamic language and you have a code base that scales and a team that scales, how things become brittle and unwieldy, and there's all these problems, and they use that as a big argument for statically typed languages. And a lot of these arguments are fair, and we did see a bunch of issues when we grew the code base and team and overall system in Prismatic using Clojure. And there are real problems with type issues that'll come up in production, but also a big part of it is just at the time of coding, of authoring code. You come into a file, you see a function, and you're not sure what it takes. You see parameters, but you don't know what the type or the data shape is of these things that you're supposed to be passing in. And so people will rely on doing this in comments or other things, or type hints, but then type hints are like somewhat limited. And so we found that it's not just about a problem of, a verification of code for robustness in production and whatnot, but even just like at authorship time, being able to know, what is this function actually taking as parameters? What's it actually returning? And you shouldn't have to go through and follow and read through the function and see what's going on. You shouldn't have to rely on just docstring for doing that. And so Schema was a practical way for us to very quickly solve a lot of the worst problems of not having a type system. Um, and it was pretty fast to do, and it all used macros. And so, this is really the beauty of the old school Lispy kind of macros based approaches. Feels like you can bake things into the language. So I think Schema is a good example of that. Um, and that's one very important part of bottom up programming. Another one is Graph, and Graph is a library that we developed, which basically just allows you to compose a function of graphs at config time to control how you're going to execute that graph, and therefore allows you to wrap all the functions in the graph with different things, so you can instrument all these functions in a particular way, so that now if it blows up, we're going to write what blows up and the stack trace somewhere. We're going to wrap these functions in sort of retry logic, so we have different robustness that we can wire in a very consistent manner without affecting any of the underlying code at all. So now if I have some code um, that is in a function and I want to test it, I can test it very easily in a unit testy kind of way. And if I want that to be retried or instrumented in particular ways for production, I can now just deal with that over at the point where I'm wiring up and configuring that code to be run in production. All the policy around that can be separated out from the code that's actually just doing something and writing to the store. And so Graph is allowing you to act away all these different details about how the code is executed without coupling your system and libraries to particular tools for instrumentation or other things like that. It's all abstracted away. And so I can have a policy for how I instrument something or retry something. And that policy can be arbitrarily changed, like just within that higher order function that's wrapping everything in the graph. I don't have to affect anything else. The other thing that's important about how we used Graph, and I think is a really good illustration of like good bottom up design thinking, is that we use the same thing for batch, for online streaming, and for like the app framework and web service backends. So sometimes people will have these systems where you're coupling to one big framework thing for batch offline processing, another thing for online stream processing, another thing for your app serving up your web app, and now you have like several different pretty heavyweight frameworks, all with different like paradigms that you're coding to within one system. And with Graph, it's just the same thing. You're always building a set of functions that you want to wire together into some graph and execute it, and that's it. And so it doesn't matter. It could be the backends to a web app. It could be a big batch pipeline that writes to a data store. It could be a streaming pipeline that doesn't write to a data store. Instead, it publishes on some channel. So there's all kinds of different options from just this one simple abstraction. And if I write a bunch of code to do a big offline processing job, and a huge number of the functions in the overall graph are the same as what I need to do online, but there's a couple changes, then it's easy to just reuse everything. It's just in my config. So in this way, you can really abstract away as much as you possibly can and just only bring in the new parts that you need. Even if the things that are being used are across different service types, like batch versus online versus part of a web server backend. So I think that's really the beauty of this bottom-up approach, is that everything is composed in as fine-grained as possible of a manner, and then reusable at config time across any of these different kinds of use cases. And you're not ever really coupling to frameworks that are particular to a certain setting, like batch or online streaming or something that is dealing with handlers for a web app. You're really working in the same way with all the different services that you're running. And so again, you're just getting maximum code reuse and simplicity. So I think that's it. That's it for the talk. Like I really just want to encourage people to look at Clojure as something that you can go very, very fast with and be very productive with smaller teams, smaller code bases, um, and then something that's can be way more maintainable, something that you can compose easily, instrument easily, deal with config as just literal data structures in your language, not have a separate weird YAML thing or whatever. Build your own simple stuff for instrumenting and observing things in prod. Leverage the REPL in prod. Like, I think that for people who've really built and run like production hardened systems for a long time, um, that's a big part of the story too. So it's the title of the talk is "Go Faster with Clojure," but in reality, it's not fast and loose. It's not this move fast and break things culture and shit's broken all the time. It's actually fast and robust and maintainable and manageable and like better from a prod perspective. So I think these are the two things that I want to like really reinforce and hope everyone takes home for the talk. Okay, thanks. Peace.